In the previous video, we're able to illustrate the result when we try to add vectors and at the same time when we try to multiply a certain scalar quantity to a vector. We have guaranteed that in that video, vector addition as well as scalar multiplication are both closed on R3. Those are the first two conditions on our axioms in order for us to determine whether R3 is a vector space or not. For this video, let's add two more axioms, and if we could of course show them here as well. So we are down by 4 already, if we again including these two, and we have a remaining 6 for the next few videos as well, because again it is also essential for us to determine whether R3 is a vector space or not. The first thing here to consider is that under vector addition, the addition must be commutative. That would mean, we have illustrated here, that if we're going to add the two vectors x and y with components here, must be equal to y plus x. This would also be true even if you're going to use the third vector, z here. And take note that all of the vectors x, y, and z are all elements of R3, so that we can actually look into the R3 as a space itself. Now, the second one is associativity on vector addition. Okay, when we try to regroup, okay, vectors under addition together with the other one, we will have the same result. So we're going to illustrate these two axioms or conditions here for vector space if they are actually true, considering the illustration or how to add vectors. Let's start with commutativity. We are asked to determine whether the sum of x and y vectors would yield into the sum of y plus x. And if we can show that, that means commutativity for vector addition holds. We could start by, of course, illustrating the expression or equivalent form component-wise for x and y vectors. We are given here with x sub 1, x sub 2, sorry, that's actually comma, x sub 3, and we're adding it with y sub 1, sorry, again, we have here y sub 2 and y sub 3. Now, when adding vectors, we learned that it's actually adding the components component-wise, meaning the first component to be added with the first component of the second, second by second, and third by third. And that means we will have the result in this notation here. So this would be x sub 1 plus y sub 1. That would be the first component of the sum, and x sub 2 plus y sub 2, the second component of the sum, and x sub 3 plus y sub 3, the third component of the sum. Now from this here, we're going to illustrate that the possibility of coming up with y plus x vectors later on, considering that the results here are actually real numbers in nature, because the components of vectors are of course real numbers as we discussed it before. Now, what we could do here is actually, since they are all real numbers, we're talking about x sub 1, x sub 2, x sub 3 together with y sub 1, y sub 2, and y sub 3, we can now commute each component. Okay? That would mean we can actually rearrange them, having y sub 1 plus x sub 1, second component y sub 2 plus x sub 2, third component y sub 3 plus x sub 3. They are just the same, because then again, these two, they are actually real numbers, and if we're going we have already commutativity for real numbers. That is true for that, and similar for the rest of the components. We're doing this because after this, we have identified that the first terms of each components are actually components of our y. We can actually break this into the form where we are going to include here all the y's, y sub 2, y sub 3, to be added with the second components or second terms of each component. You have x sub 1, x sub 2, and x sub 3. And what does this tell us? What is this vector and what is this vector? It's actually equivalent to y plus x. Hence, we have shown here that x plus y is just equal to y plus x. Then, commutativity holds for vector addition. That is additional axiom that we have verified or satisfied in the context of determining whether R3 is a vector space or not. Now, this is true, so later on, if we're going to talk about some vectors as well in R3, we can of course commute them anytime, because commutativity for vector addition holds. Now, for the second property for this video, let's try to show associativity for vector addition. So similarly, we'll work from this, and hopefully we could reach to that portion there. So let's start with the sum. Okay, we'll have here x plus y, then plus z must be in return to this. Using the components there, we'll actually have the first group you have here for your x sub 1, x sub 2, x sub 3. Take note, I'm using bracket because it would involve two different vectors first. So you have plus y sub 1, y sub 2, y sub 3. Then we will add here the components or the vector z. You will have here z sub 1, z sub 2, and z sub 3. Okay, so from this now, let's work by adding first or combining all the components here. So you will have the form, okay, still in brackets, x sub 1 plus y sub 1, x sub 2 plus y sub 2, x sub 3 plus y sub 3, as we add the components of vectors x and y as a group. Plus, you will have here z sub 1, z sub 2, and z sub 3. Now, treating this as one term, and this one term as well, and one term as that, of course, we can, add this with the remaining vector z. This would be its form. Okay, you will have here, you have x sub 1 plus y sub 1 plus the first component of the second term, z sub 1. Take note, it's still in a grouping because we have there as a group. Okay, we will try to look into that later on. The second would be x sub 2 plus y sub 2 plus your z sub 2. And finally, you will have here x sub 3 plus y sub 3 plus z sub 3. Now that we are done doing this, take note that we now have a vector, of course, in R3 as well. Regardless of what will be the result or the values for x sub 1, x sub 2, x sub 3 together with y's and z's, because they are all real numbers, then basically we will have the same result as a vector in R3 as well. What we need to do here, and since all of these components will have real numbers in nature, we can now associate the terms in each component. Meaning, we can actually do it like this, where instead of x sub 1, y sub 1, I'm going to let x sub 1 in itself, plus y sub 1, and plus z sub 1. This is possible because associativity for real numbers is actually true. That means this is applicable here because x sub 1, y sub 1, z sub 1 are also real numbers. Similarly, you have your x sub 2 plus y sub 2 plus z sub 2. And for the third one, leaving x sub 3 in itself plus y sub 3 plus z sub 3. Okay? That is the next part of the proof. Now, leading towards our goal of having this one here, we can see when we treat this as one term, we can take out the first components as one vector and the other components, which are actually a combination of two, as another vector as well. So we could have this form here, x sub 1, x sub 2, x sub 3, taking out all the first components because they form a certain vector, plus we have the second group composed of the sums. Okay, so I may remove the grouping symbol here, or just to be similar with what we did here earlier, specifically on this step, let me try to, of course, add the same. Okay, just for the purpose of the proper illustration. For the second one, y sub 2 plus z sub 2, and the third one is y sub 3 plus z sub 3. Of course, you can remove parentheses if you would like to. Okay, now this time, we can see that this is already our x, and what we need to do here, this is already okay to show that this portion is also true. Looking to that, we can see here that all the components also starts with y's, and the seconds would be z's. So we can have it like this, x sub 1 still, x sub 2, x sub 3, plus taking out the first components, y sub 1, y sub 2, y sub 3, plus the second component, z sub 1, z sub 2, and z sub 3. Notice that we still have the brackets because it stands for this group as a whole. We're just breaking it into two portions, but they are under the same group. Now for this, we can now work towards the forms because the first form is just actually your x plus your second here. Let me use parentheses this time because we will have the vectors y plus z. Now we have shown, okay, that if we're going to have x plus y before your z, or your capital letter Z, this is just equivalent to x plus y plus z. By the way, I have here this form just to show, okay, that our proof is done, or not there. I'm gonna paste it here. So we have shown that associativity for vector addition also holds, together with the first, which is commutativity, and together with the first video or the previous video talking about closure property for vector addition and scalar multiplication. We do now have 4 of the 10 axioms in the process of determining whether R3 is a vector space or not. At the same time, the point of this video, when we have vectors later on in R3, or specifically for in a sphere, as we talk about geometry of the sphere, we can always apply commutativity and associativity for some addition processes that will be involved in that concept. Thank you very much for watching.